What did you say?
When did we come to lecture 4? We covered them all. Last time, 3 lectures.
Yeah. He was sleeping. So. Okay, welcome back to EE210B. This is our course on inference over networks. And today we will continue our overview of background material, right, in this lecture and perhaps some of next lecture. And afterwards, we will start discussing networks and processing over networks in greater detail. Okay, so these initial lectures are meant to prepare you with the tools that we will need to study these networks with some depth. Okay, so today I will be talking about convex functions. You may have seen convex functions before. If not, this is your opportunity to know what they are. Okay, now one extension that I do here that you may not have seen before is that I'm going to define convex functions for both cases when the argument is real valued and also when the argument is complex valued. Okay, and the reason I do that is because it's not uncommon in signal processing and communications applications to encounter problems where the unknown that you are interested in, the argument is actually complex valued, whether you are solving an estimation problem, a beamforming problem, an antenna array problem. So it's not unusual for the unknown that you are interested in to be complex valued. Okay, so that's why I also talk about extensions to the complex case. And like you saw last time, dealing with complex valued data can introduce some specialties that you don't encounter in the real case. For example, some special situations, that you don't encounter in the real case. I showed you that the Hessian matrix of a function g of z, right, where z is of size m, will be 2m by 2m, and it's not always block diagonal, right? It will have a 2 by 2 block structure. And when this block structure is not block diagonal, that will introduce, right, coupling among the variables z and z star, as you're going to see later in this course. Okay, so it does help to look a little bit closer at what happens in the complex case, and that's what I will be doing here. So let's continue. So this is the reference for this lecture. Okay, it's Appendix C from the text I mentioned to you last time, which you can access on my website. Okay. So again, the setting is the following. I have a function, and like I said, 90% of the time or more, our functions will be real valued because these are the cost functions. For example, a quadratic function, a logistic function. You will be seeing examples of this later. So the function will be real valued, okay, and the argument will be a vector in general, right? I have a cost of a vector argument, but that argument can be complex or real. That's what I meant by a complex argument, okay? Let's first consider the case of real arguments and define convexity for functions of real arguments. That's what's most commonly done in the literature. That's what you would find more commonly in the literature. Now, in my presentation here, each time I need a derivative, right, a first order gradient or a second order Hessian matrix, right? I'm assuming that they exist. If I write down gradients or Hessian matrices, that's because I'm assuming that whatever first order derivatives that you need, partial derivatives that you need relative to the real part of z, the imaginary part of z, and so forth, that they exist, okay? Very good. So that's my setting. This is my function. Okay, and these are the partial derivatives that I'm going to assume they exist whenever needed, first order or second order, relative to the real and imaginary parts of z, right? That's what x and y mean, right? Z is x plus jy. Okay. So So like I said, I'm going to distinguish between two cases. Let's start with the real case, and then the extension to the complex case will come next, okay? Very good. So let's start with the real domain, okay? Real domain, so Z is a real vector of size M, a column vector, okay? So before I define what a convex function is, let me first define what a convex set is. Again, like I said, most of you have seen this probably in the real domain, so this is a refresher for most of you, right? So a convex set, right, is a set of points that has the following property, right? The set has the following property. If you pick any 2 points in that set, any 2 vectors in that set, and you compute a convex combination of these sets, that's what this combination ends up being called, right? Alpha and 1 minus alpha. So alpha is a non-negative number. Therefore, alpha and 1 minus alpha add up to 1. That convex combination will also be in this set. Okay? So the geometric interpretation of this is that if you pick any 2 points, Z1 and Z2, right? Any point that lies on the segment connecting Z1 to Z2 is a point given by a combination of this form. For example, when alpha is 0, you get Z2. When alpha is 1, you get Z1. When alpha is 1/2, you get a point in the middle. So all the points in between are described by this combination. And what this is saying is that if Z1 belongs to the set and Z2 belongs to the set, then if the set has the following property, any point in between belongs to it, it's a convex set, right? So this is a figure here. So the 2 sets on the left, they are convex sets. If you pick any 2 points and you join them by a line, all the points in between lie inside the set. So this is a convex set, okay? And the same thing here, right? But not here. And you have the example there, right? If you pick these 2 points and you connect them, you have a whole range of points on that segment that do not belong to the set, right? So you understand what a convex set is. Very good. Okay, so now what is a convex function? Okay, so a convex function, as you know, whenever you define a function, g of z, there is a domain associated with the function, right? That's the set of points over which the function is defined. So we assume that the domain itself is a convex set, right? So a function, for example, right, is defined, let's say, from a segment into some other location. So this segment is convex. So let's assume that the domain of the function is convex. Okay, so this is usually the case, at least in the situations that are of interest to us. Okay, so the domain of the function is denoted by this notation, domain of G. Okay, so what do we mean by a convex function? This is the definition. If you pick any 2 points in the domain of the function and you evaluate the function at a point on the segment, right? This is G evaluated at a point on the segment connecting these 2 points. Okay, so the value of the function at that intermediate point is always upper bounded by the convex combinations at the endpoints. Okay, so let me show you a figure which will illustrate this. Okay, so what this means is the following. Okay, in this figure here, I have a convex function. This blue curve is a convex function. It's a function of the variable z. Let's pick 2 points, z1 and z2. So this is g at z1, and this is g at z2, right? Let's now evaluate g at any point in between, right? So this point here is a combination of z1 and z2, so it lies on that segment. And if you evaluate the function at that point, right, what the definition of convexity said is that the value of the function at that point, right, is smaller. Now what is this? If you take a segment that goes from g of z1 to g of z2, right, here it is. This is a segment that goes from g of z1 to g of z2, right? The right-hand side is a point on that segment, right? So what the definition of causality is saying, of convexity is saying, is that the value of the function at any intermediate point on the segment will be below, right, the segment connecting the values of the function at the endpoints. That's what it means. You understand the definition? Okay. So this is a convex function, If you evaluate it at 2 points here and there, right, then the value at any intermediate point will be lower than the value on this segment connecting the value of the function, the values of the function. That's what convexity means. Whenever you have that property, then your function is convex. Most of the cost functions, almost all of them that we'll be dealing with in this class will be convex. Okay, so that's why this is a very important property. And the reason why we study mostly convex functions is because, as you're going to see, they have very useful properties, very nice properties. Okay, I'm going to be listing many of these properties here, okay, in this lecture. So that's convexity, okay? Fine, you understand this definition? Okay, very good. Now, there is an equivalent characterization of convexity. This is a homework problem to show. I showed you one definition. G at an intermediate value, right, lies below the segment connecting the end values, right? Another equivalent, and this is an equivalent characterization of convexity. Of course, when I write this expression, I'm assuming that in this particular form that the function is differentiable, right? The gradient vector. This is the gradient vector we defined last time, right? Okay, the one that we defined last time, okay? So this gradient vector here, okay. So what this equivalent characterization is saying is that for any 2 points, z and z0, the value of the function, of the convex function, is lower bounded by the expression you have on the right. Now let's look at the expression you have on the right. You all agree that this is the equation of a hyperplane, right? In one dimension, this is the equation of a line, right? In one dimension, right? This is the equation of a line. When z equals z0, the value of that hyperplane is g at z0, right? So this is a hyperplane or a line that passes through the point z0 and g of z0, right? So if you go back to the figure, here it is. This is your convex function. And this is the equation actually of the tangent to that function at location z0, because you see, just think about it in terms of one dimension. What's the slope of that line, the gradient, right? So what this equivalent characterization of convexity is saying, it is saying that the function, the convex function, right, is always bounded from below by the tangent, right? At the okay, by the tangent at any point g0, right? This is the gradient z minus z0. Remember that we define the gradient relative to a column z will be a row vector, right? So this is actually an inner product, row times column. So you have two equivalent characterizations of convexity which are captured by these two figures. To show that if this holds, that holds, or vice versa, this is a homework problem. It's not a difficult homework problem. It requires some argument, but you can do it. You understand? So these are two equivalent characterizations of convexity, this way or that way. You can think of it either way. This second definition will be very useful. Okay, it essentially tells you that given a convex function, I can always underestimate it, find an underestimator for it, find a linear function, a hyperplane that, right, approximates it from below. That's a useful characterization, okay? So let's move on. Okay, so now why are convex functions so useful? Because of this property, okay? If a convex function, okay, if a convex function has a minimum, right, it can only be a global minimum. It can only be a global minimum. It doesn't need to be unique, right? It doesn't need to be unique. Okay, for example, this is a convex function, right? Okay, this is a convex function. It has multiple global minima. Okay, so if it has minima, the minima have to be global. You cannot have local minima or local maxima or saddle points, right? Very good. So this is one property of convex functions. I'll have more to say about this later. Okay. Now, another useful property of convexity is this relation that you have here, which you will be using many times. Okay. And what this relation says is the following. If a function is convex, pick any 2 points, compute the gradients at these 2 points, right? So you end up with 2 vectors, right? You end up with 2 vectors. One is the difference between the 2 points, and the other is the difference between their gradients, okay? So what this property is saying is that the inner product is always non-negative. Essentially, these vectors will always be pointing in the same direction, right? That's what this is saying, right? If the 2 vectors are pointing in the same direction, their inner product will be non-negative. So this is this goes in one direction, okay? So if your function is convex, remember this because this property we will use it later. I'm going to prove it. It's not difficult to prove that the inner product is non-negative. Fine? Okay? Okay, so let's continue. This is the proof. Let's prove it. Pick any 2 points, Z1 and Z2, right? Remember, this is the definition of convexity, that the function at Z2 will be lower bounded by the plane that's tangent at Z1, right? Because that property holds for any 2 points. And likewise, the function at Z1 is lower bounded by the plane that's tangent at Z2, right? So these 2 properties have to hold because this is equivalent to the definition of convexity. So now if you take the second line, here you have G of Z1, put it up here, right? So if you take the second line, because this is larger than the right-hand side, and then G of Z1 is larger than this, so replace this there, right? You will get G of Z2 is larger than or equal to G of Z1 of Z2 again, plus this plus that, right? G of Z2 will cancel from both sides, and you will be left with this plus that, right? Being less than or equal to 0. If you group these 2 terms together because they have a common term, Z2 minus Z1, right? You get that relation. You understand? So the proof actually is not difficult. You get this property here, okay? So this is a useful property of convex functions, okay? Whenever you take 2 points, compute the gradients at these 2 points, and then compute the inner product between the differences. These inner products will have to be non-negative because these vectors will have to point in the same direction. And you will see later why these results are useful. Yes?
This result doesn't seem correct because I think of an example, let's say a circle, right?
Yeah.
And this result says that if Z2 is greater than Z1, then the slope at Z2 is greater than slope at Z1.
Sorry, if Z2 is?
Greater than Z1.
Yeah.
So Z2 minus Z1 is positive.
So you're talking about the scalar case?
Yeah.
Yes.
So if Z2 is greater than Z1, then the difference in the slopes must be positive. That means the slope is increasing. That's what this result says.
Yeah.
Right? But if you take a circle, if you take Z2 to be point on the right, where the slope is decreasing, and Z1 to be point on the left, where the slope is actually increasing. So the slope on the right minus slope on the left will be actually negative.
I didn't follow your example. Okay. Sorry?
So convex function like a circle.
Sorry? Yeah.
So you will take a concave function.
Okay, anyway. Yeah, I did not follow your example very clearly. So you are talking about what?
Scalar case.
G, not scalar case, x1, x2.
Yeah,
Right, so you are talking about G of xy equals x squared plus y squared, the function like that.
Yeah, less than or equal to some value. Yeah, G of xy equals x squared plus y squared, yes.
Okay, so this is what you are saying. This is the norm of z squared, right? So this is a quadratic function, not a circle. In the z domain, this is a quadratic function, right? In the z domain, let's look at it. So this is g of z, right? In the z domain, I'm talking about the z domain. Okay, in the z domain. Okay, these will be vectors now. These are not scalars. These are the xy together. Okay, so in the z domain, g of z is, in the example you are giving me, g of z is z squared. Okay, so what is the gradient of g? Okay, so this is what? Z transpose z. So let's differentiate relative to, what do you get? 2 z transpose, right? Something like that, right? So you will see that if you pick any 2 points, this difference will be z2 minus z1, and this difference here will be 2 z2 minus z1 transpose. So the inner product will always be non-negative, okay? Right? So for this function, this quadratic function, this holds. Remember, these are the vectors, okay? The x, y. Very good. So let's continue. Okay? So I showed you the proof, the argument, okay? Now, so far, and most of the time in this course, even though many of these results can be extended to this case, I will be assuming that the cost function that you are interested in is differentiable, okay? The cost function is differentiable. But there are situations where the cost function may be not differentiable at some points. For example, let's assume z is a scalar, and let's take the function g of z equals the absolute value of z, right? So this particular function is not differentiable at 0, right? So how do I define convexity in this case, or at least how would I, of course you can't define convexity, right? The first definition is applicable, but I'm talking about the second property that involves bounding the function from below by a hyperplane where the gradient vector used to appear here. But now, if this point z0 happens to be a point where the function is not differentiable, right, what relation would I use instead of that, okay? So this is where the notion of subgradients comes in, okay? The notion of subgradient, okay? So let me first define what a subgradient is. What a subgradient is, and by the way, subgradients at a particular point are not unique. You can have many subgradients. What a subgradient is, okay, so if g is a convex function, okay, and z0 happens to be a point where the function is not necessarily differentiable, like 0 in this particular example, z0 equals 0, okay, then a subgradient is any vector y, right? In this particular case, I chose it to be a row because the gradient was a row. Any vector y that makes this inequality hold. That would be called a subgradient. You understand? That's the definition of a subgradient. Any vector y that you can use here in place of the gradient vector, which doesn't exist in this case. Of course, this inequality may be satisfied with the true gradient here at points where the gradient exists. But at points where the gradient does not exist, a subgradient would be any vector y that you could put here and satisfy the inequality, okay? Now, so we often use this notation here, okay? Partial g at z0 to denote the set of all possible vectors you could pick. I'll show you an example very soon. Sometimes people just use the partial of g here. This is just a matter of notation and convenience. But when they do that, what they really mean is one of them, right? So for example, take this example here. Okay, take this example. This is a function, the blue function. Is it convex? Right? It's a convex function. If you go back to the graphical interpretation we had before, pick any 2 points, right, on the function, connect them, that gives you a segment, and evaluate the function at any point in between. It should lie below that segment, which is true in this case. So it is a convex function, right? From definition 1, I don't need to introduce gradients and subgradients to know that, right? It is a convex function, okay? But the question now, what about that second property, right? The second property. For me to write it down, I need to, for example, if I want to write it down at this point z0 where the function is not differentiable, right? I cannot write it down because the gradient is not defined. However, in this particular case, right? In this particular case, if you remember, if I have a convex function that's differentiable, right? The gradient at any particular point is related to the direction of the tangent at that point, right? In this case where the function is not differentiable, I can have many possible tangents, right? I can have a range of slopes, right? I can have a range of slopes. For example, let's take this simple example that you are familiar with, the absolute value function. If this is x and this is absolute value of x, right? This slope here is -1. That slope there is 1, right? So at this point here, you can take any line, right, with a slope, let's say, ranging from -1 to 1, and it will be a valid subgradient, right? In this particular case, any value, any number you choose between -1 and 1 can be a valid subgradient at 0. Okay, understand? So that's what a subgradient means. Now, we will not be dealing with subgradients in this course, but what I would like to say is that many of the results that we'll be discussing, they can be extended. They can be extended if you replace gradients by subgradients and pay attention to some technical details that come up in the derivations, okay? Very good. So let's continue with the differentiable case. Continuing with convex functions, the following are some useful properties. Useful properties. If g of z is convex, right, and then you perform an affine transformation, you replace, let's say, z by az plus b, let's say z by 2z or z by some matrix times z plus a shift, the result is still convex, okay? So affine transformations do not destroy convexity. Proof, it's not difficult to prove. This is left as an exercise, okay? If you have two convex functions, g1 and g2, each one of them is convex, and then you plot the function that's the maximum at each point z of both, that result will also be convex. Again, it's not difficult to prove, okay? Go back to the definition and it's easy to prove, okay? And any combination of convex functions where the coefficients are non-negative is also convex, right? So these are useful properties because we'll use them. Not difficult to prove, right? Just go back to the definition, right? The first definition, apply it in each case, and you will see that these are convex functions, okay? Fine, so let's move on now to a stricter notion of convexity, which is strict convexity, right? I will be talking about convex functions, strictly convex functions, and strongly convex functions, okay? These are three notions, okay, with the definitions becoming more strict as we move from one class to the other, and you will see what these additional requirements imply, okay? So what is a strictly convex function? A strictly convex function, the definition of it is just very similar to convexity. This is equation 10 that you have here on the slide, except that the inequality sign is replaced by strict inequality. That's it. If you evaluate the function, right, at any middle point, that value of the function will definitely be strictly lower than the segment connecting the values at the endpoints. It has to be strictly lower, right? Okay, so for example, is a function like this strictly convex, right? If I pick, for example, this point and this point, right, the segment connecting the values of the function will be exactly that segment, right? And so this is not strictly, it is convex, but not strictly convex, okay? So that's the definition of strict convexity. So what does strict convexity imply that's useful for us is that now if a minimum exists, okay, it has to be unique. Before, for convex functions, you can have multiple global minima. For example, this function here, right, right? This function here has infinitely many global minima, right? For strictly convex functions, the global minimum will be unique, okay? That's a very important property. That's why we are interested in strict convexity, because if you are seeking a minimum, you know you are looking for something that's uniquely defined and you hopefully can converge towards that point, okay? Very good. So the minimum will be unique, okay? And what about the inner product property I mentioned to you before? For convexity, if we take any 2 points and you compute the inner product with the gradients at these points, that inner product was larger than or equal to 0. Now it becomes strictly larger than 0. That's all. So for strict convexity, essentially the inequalities become strict inequalities, okay? So again, you can establish this in a manner very similar to what we did before. Okay, fine. So that's strict convexity. I'll give you examples very soon. Okay, I'll give you examples. I'm introducing the definitions. So when I move from convexity to strict convexity, I now ensure that the global minimum is unique. That's something good for us. But now I'm going to go a step further and talk about strongly convex functions. Okay, so what is a strong convexity? Okay, it's a stronger notion than strict convexity, right? Otherwise you wouldn't use the name strong, okay? So again, so the function is strongly convex. Actually, to be more precise, we always attach a label to it and say nu, or whatever symbol you use for that, alpha or mu or nu. I'm using nu just because mu and other symbols are used for other things in these notes, okay? So nu strongly convex, what does it mean? Okay, it means that, again, you see, this is the definition of convexity that we saw before, right? The value of the function at a middle point has to be below the segment connecting the endpoints, okay, with some margin, right? That's essentially that you will be lower than this by some margin that depends on that parameter nu, okay? That's all. So you have some margin below this, okay? So this is called strong convexity, right? And the margin, right? The margin is quadratic, depends on the difference squared, okay? So this, okay, so now this is the definition of strong convexity. Let's see what this implies. And I'll give you examples again. Okay. So you can see that, again, this nu is positive, is a positive number, right? So if a function is strongly convex, it is necessarily strictly convex, right? Because you are subtracting, for z1 different from z2, right? You are subtracting something positive here, right? So strong convexity implies strict convexity, okay? Therefore, strongly convex functions also the minimum, the global minimum is unique. It can only have a global minimum and it's unique, right? Just like strict convexity. So far, so good, right? So strict convexity and strong convexity imply that the cost function has a unique global minimum. No other local minima, local maxima, and so forth, okay? So far, so good. Now, why is this useful? You will understand, okay, hopefully very soon or in next lectures, okay? So here it is. Strong convexity implies strict convexity, which implies convexity. Fine? You understand that? Okay. Now, so when you put it in this way, it does mean that there are some functions that are strictly convex but not strongly convex, okay? For example, this function here, z to the 4, okay? Let's start with z squared. Z squared is the parabola, right? I'm going to show you very soon, give you a way to check whether a function is strongly convex or not by looking at its Hessian. Essentially, if you look at the Hessian matrix, in this case, in the scalar case, you look at the second order derivative. What's the second order derivative here? 2. If the second order derivative is bounded away from 0, then it is strongly convex. I'll show you the statement very soon. So this function is strongly convex. But this function is not strongly convex. To prove that this is not strong, it is strictly convex. To prove that it is strictly convex, again, this is a homework problem. Just go back to the definition. Apply the definition of string convexity to this. You'll be able to conclude that it is strictly convex. So this is an example of a function that is strictly convex but not strongly convex, okay? Now, let's look at a plot. Yes.
First order condition for the strong convexity, you have the parameter alpha.
Yes.
But if you evaluate then the Hessian, the second order condition, the alpha disappears. So what?
No. Okay. These are two different things. Okay, two different things. This is just a definition of convexity. What this is saying is, if I evaluate the function at any convex combination of the arguments, right? The value of the function at this middle point or point in between has to be below, right, the segment connecting the endpoints, okay? For any alpha, which means for any point you choose within that segment. So this is one way of defining it. The Hessian condition is a condition that I'm going to show you. It will be equivalent in some cases. There's another way of checking whether the function is convex or not. It doesn't have any alpha in it, okay? It's just the Hessian matrix calculation, okay? But before I get to these Hessian matrix calculations, let's look at this example. So if you look at the plot on the right, so the class of convex functions is the bigger one, right? The bigger ellipse. Strictly convex is smaller and strongly convex is smaller, right? So you understand this. Here on the left, I have a plot of two functions, z squared and z to the 4, okay? I claimed to you that z squared is strongly convex, z to the 4 is strictly convex but not strongly convex, okay? How do you prove it? Just go back to the definition. You have to do this small calculation to convince yourself, okay? It's not difficult to do, but for now, believe me, okay? Or for example, for the z squared case, we can apply the Hessian test that I'm going to show you very soon and you will be convinced, okay? But if you go back to the definition, z squared is strongly convex, that's the red curve. And z to the 4 is strictly convex but not strongly convex, that's the blue curve, okay? So you observe already that for strongly convex functions, the function, right, is more concentrated close to the minimum, right? Whereas you have a more flat opening for functions that are not strongly convex. So you can see if you are using iterative algorithms to locate the global minimum of a strongly convex function, you will have an easier task to do so than if you are doing it for non-strongly convex functions. Convex but non-strongly convex, right? Because this is more flat, right? And this is more, right, a sharper, you have a sharper minimum, right? So this is a useful, so strongly convex functions have this nice property, which is being illustrated in this plot. So, and we are going to see when we study iterative algorithms for adaptation and learning that this property will be exploited to great effect, okay, to study the convergence and stability of these algorithms and so forth. We are also going to give statements about convergence in cases where this is not strongly convex. You can also do that, okay? But let's leave that until time comes, okay? Let's just focus on what strongly convex and convex functions are, okay? Now, just like you had it for convex and strictly convex, we were able to bound the function by hyperplanes from below. A similar thing holds here for strongly convex. You can also bound the function by this hyperplane plus an additional quadratic term, okay? Plus an additional quadratic term which grows with z, okay? So what does this mean? It means, you see, as the value of z, you see, remember, this is a function here, right? And this is the hyperplane. This is the point z0, right? So what this was saying for the complex case, forget this last part for now, is that at any point z, the function will be above that line, right? For strongly convex, it's telling you that you will be above that line with a sufficient margin, right? With a sufficient margin that actually grows with the square of the distance of z to z0, right? So if this z here is far away from z0, so this margin here is growing quadratically with that distance, okay? This is another way of saying, think of it like this, you see? This is another way of saying that this function looks more like this rather than a flat function like this, right? Because for this distance here to grow quadratically with z minus z0, the function, right, has to look more like this with a sharper focus at the minimum than like this, right? So this property is explaining the behavior you observed in the previous plot, right? Okay. Very good. Now, another conclusion you get from here, Z0 here denotes an arbitrary point, okay? In my notation throughout this course, whenever I put the O on top, that's a special Z, right? That's a special argument, that's the minimum. Whenever I put this little O on top of something, then that argument is a special thing, okay? So Z with an O on top, right? Superscript. This is the minimum of G of Z, the minimizer. The point where it is a minimum, okay? So if I pick Z0 to be the minimizer, what will happen here? Okay, so this disappears, right? So you will get that this is larger than this plus that, right? Okay, so for that particular case, right? This is telling you how the value of the function is growing relative to its value at the minimum, right? Faster than a quadratic. Again, this brings in that idea, right? That it's growing fast. So this is a plot here. You see, this is a plot. This is the minimum, right? And this is G at any point Z1. This is G at Z0. This difference here grows larger than a quadratic. You understand? That's all, okay? Very good. So these are properties of strong convexity. Okay. And what about the inner product property I mentioned before? What's the difference now? The difference now, if you pick any 2 points and compute the gradients and the inner product, it's sufficiently away from 0. You see? Now you have, this is a non-negative number. If Z1 and Z2 are different from each other, this is a positive number, right? Okay, so you have, before it used to be 0 for convex, strictly larger than 0 for strictly convex. Now it is larger than or equal to this value here, okay, for strongly convex. Fine? Very good. So this is a summary, okay, of what we have done so far, okay? A summary of what we have done so far. And the reason I summarize these particular properties is because we are going to be using them, okay, multiple times in our derivation. So just remember, right, when I'm going through my arguments in the future, okay, when I have cost functions that are convex, and we will encounter inner products like this involving differences and gradients at these points, right? I'll tell you, remember, this inner product is non-negative, or this inner product is strictly positive, or this inner product, I can remove it and lower bound it by something that depends on the quadratic, right? So that's where it comes from this table, okay? So it's a useful table to keep in mind. I will remind you when we get there, okay? But the first conclusion from this first part of the lecture is this table, okay? Remember these inner product properties, okay? Very good. So now, how do I check whether a function is convex, strictly convex, or strongly convex? Well, number one, go to the definition. Always go back to the definition, right? Which says if you evaluate the function at a convex combination, that's upper bounded by the convex combination of the g's. The second one, go to the equivalent characterization, right? Which says, for example, for convex functions, that the function is lower bounded by the tangent at any point, right? Another one would be to use these properties here in terms of the Hessian matrix. You can show, of course, I'm just stating them here, okay? You can show that a function is convex if and only if the Hessian is non-negative definite. For example, z squared, the Hessian was 2, right? Okay, so it's convex. Z to the 4, the Hessian is 6z squared, again larger than or equal to 0, right? Very good. For strongly convex, before I talk about this, look at strongly convex. For strongly convex, you don't only need the Hessian to be positive definite, it has to be sufficiently away from 0. Okay? And that in U is this nu. So when you say that a function is nu strongly convex, you are saying that its Hessian matrix is sufficiently away from 0 by that amount in nu. And this will be very useful for us, okay? You are essentially saying the Hessian matrix is bounded from below, right? Bounded from below. So if you need to invert it, for example, it is invertible. It's not the case in the first, right, situation, okay? So just remember that. So strong convexity actually adds a lower bound on the Hessian matrix, right? You see it from this property. Now, in the middle line is not an if and only if relation. That's what I wanted to say. The arrow only goes in one direction, right? You see here? So if the Hessian is strictly positive, definite, then it is strictly convex. So let's take the example z to the 4. Z to the 4, I claim that it is a strictly convex function. What is the Hessian? He said it, 6z squared. It's not greater than 0 for all z, for z0, right? But it is strictly convex. So you see, the other direction is not correct. It doesn't always hold, okay? So how do I prove that z to the 4 is strictly convex? You cannot use this. You have to go back to the definition, okay?
The definition is necessary and sufficient.
Yeah, of course, that's the definition, right? The definition is necessary and sufficient because it is the definition, okay? Okay, so let's move on. Okay. Let's take this quadratic function, okay? The quadratic function. Is it convex? Sorry, is it strongly convex, for example? What's the Hessian matrix here?
C.
No? 2C, right? I told you last time not to forget the 2, right? 2C. 2C is lower bounded by 2 lambda min of C, right? The smallest eigenvalue of C. Here I'm assuming C is symmetric and positive definite, right? I'm telling you that. C is symmetric and positive definite, right? You see it here, okay? So it is nu strongly convex, and what's the value of nu? 2 lambda min of C, right? So quadratic functions where C is positive definite and symmetric are necessarily strongly convex, okay? Very good. And we know the value of nu. Now this other cost will come up often, okay? If you have taken 210A, right, the course on adaptation and learning for single agents, you saw this when we studied logistic regression, right? When we studied algorithms to perform pattern recognition or pattern classification, right? Cost functions like this come up. For now, you just need to know that a cost function like this comes up. You have a quadratic term in z here, and the log of a term that involves an exponential. Gamma and z are vectors. As a function of z, you can show that this function is strongly convex. One proof is there. If you compute the Hessian relative to z, okay, here you will get rho I. Here, right, compute the gradient relative to z. You can compute the gradient of the inside. And then remember, this is a log, right? So you'll have 1 over this times the gradient of the inside relative to z. The gradient of the inside relative to z, you see, the z is a column, so you'll get, you will get what? You will get h transpose times the exponential, h transpose times the exponential over, right? Over that, and then you have to compute the gradient relative to z transpose again because you want the Hessian, right? So these are 2 successive gradient steps. If you do that calculation, this is what you get. If you look at it, you see this is strictly positive definite, right? This is non-negative definite, right? A vector times its transpose. This is a positive scalar. So this is definitely always larger than rho I. So the logistic regression cost that you see here, I'll explain to you later how it comes up in the context of machine learning. So this cost function is strongly convex, right? With the rho here. Okay, if I don't have the rho, you can only say this is larger than or equal to 0, which makes it convex, okay? Very good. This is another cost function. Again, if you have taken EE to 10A adaptation and learning, you have seen this cost function, right? This is the kind of cost function that comes up when you study support vector machines, right? So if you're not familiar with that, that's fine, okay? You don't need to worry about that. I'm just giving you examples that costs like this do come up, right, in the study of learning algorithms, okay? So this cost function is strongly convex, rho strongly convex. How do you prove it? Okay, I cannot use the Hessian here because this is non-differentiable. right? This is non-different. If you plot that function, okay, it is non-differentiable, okay? However, this term alone is strongly convex. 0 is a convex function, right? This is a linear function in Z. A linear function is convex. The maximum of two convex functions is convex. So you have convex plus strongly convex. If you use this fact, you get that the result is strongly convex. So what I'm trying to say, you have many equivalent characterizations and properties of convexity. To prove convexity, sometimes it doesn't mean that you can apply all of them. Sometimes you have to choose which property to use to be able to get to the result. In some cases, you have to go back to the definition, right? Okay, these examples show that. Fine. So let's move on to the complex domain. Most of you may have seen what I talked about in the real case, okay, convex functions with real arguments. I want to extend this to the complex case. Some of you, or many of you may not have seen this because it's not that common in the literature, but I explained earlier why I would like to do this, okay? So now I let Z to be complex, right? Z can be complex, but the function itself is real valued, right? For example, G of Z is the norm of Z squared. The function is always real valued. Our costs will be real valued, but the argument can be complex. So how do I define convexity in this case? One way to do it is to think of Z as this vector xy, where x is the real part of Z, y is the imaginary part of Z, right? G of Z can be thought of as a function G of V. Now it becomes a function of a real argument, but the real argument is twice as large, right? Okay, so convexity of G of Z amounts to convexity of G of V, right? So this is the simple answer to the question, right? Think in terms of the real version of G of Z, right? Replace Z by its real arguments x, y, and think in terms of G of V, right? Instead of thinking in terms of this, think in terms of that. Then everything we talked about applies, right? Okay? So the story would end here, but it doesn't end here because all these properties I showed you before about, for example, the hyperplane that bounds it from below. If you apply the definitions from before, this hyperplane will be described in the V domain. V, right? But I want it described in the Z domain instead, so that everything is in the Z domain. The inner product inequalities that you saw here in this table, they would be described in the V domain, but I want to describe them in the Z domain, right? So I want to show you how to do that, okay? And how will these expressions look like in the complex case? You understand what I'm doing? Okay, so let's go. Okay, so first of all, remember I'm introducing Z. So Z is x plus jy, okay? So this is the map to go from x to Z and from Z to x, right? You see here, this matrix I plus ji times xy gives you Z, and I minus jy gives you Z star, and you transpose it, okay? Because Z star is a row, and then transpose it becomes a column, right? So this is just a convenient way. If you remember, I called this vector U, the vector that collects Z and Z star on top of each other, I called it U. And the vector that collects x and y on top of V, all this is saying is that the transformation is invertible, right? Because if you remember, d star was 2 times I, right? Okay. So let's look at this, okay? So I will say that G of Z is convex if the corresponding G of V is convex, fine? Which would be to say this. Right? G at any middle point is upper bounded by the, okay. But I want to transform this into a statement in the Z domain. Well, G of V is simply G of Z, right? the value of G at V is the value of G at Z. This is just the definition. So you can translate 26 into 27 directly. So this condition is not difficult to translate. So this is the definition of convexity when Z is complex. Trivial. Fine? So far, this is trivial. Just what you know from the real case. Okay? Yeah.
Only alpha must be real, right?
Yeah, alpha is between 0 and 1, right? I say it here. Alpha is between 0 and 1. Okay? Scalar, right? Between 0 and 1. Here, okay? Continue. Fine so far, so this is trivial. Okay. Let's look at this other property now, which says that this is an equivalent characterization of convexity, that G of V is bounded from below by this hyperplane, right? So we all accept this in the V domain. Fine? What is the equivalent of that in the Z domain? This is what I want to show you the argument, okay? Once you understand this argument, then this same derivation repeats itself, so then I can go faster later, okay? So let's translate this into, so G of V, this one is obviously G of Z. This one is obviously G at the corresponding Z, the Z that corresponds to V0, right? What about here? I showed you before that to go from V to U, there is a transformation, right? There is a transformation. So to go from this V to the corresponding U, if I multiply V minus V0 by D, I'll go to U minus U0, right? So if I put a D here, and then the inverse of D, right? I don't change anything. The inverse of D is 1/2 D star, because D star is 2, right? So what I'm going to do here, I'm going to insert 1/2 D star D, right? Fine so far? Then D times V minus V0 becomes U minus U0, okay? Very good, which is still not Z. It has Z in it, but okay. What about the gradient relative to V times D star? Let's look at that. Remember that V is the column vector xy, right? This is what V is. Okay? This is what V is. So V is a column. When I compute the gradient relative to V, I'm going to get a row, right? Right? And remember, how did we define the gradient vector relative to a vector? It is the vector of partial derivatives. It will contain the partial derivatives relative to the x's, the partial derivatives relative to the y's. So the gradient relative to V contains the gradient relative to x, the gradient relative to y. Fine? Fine? So now multiply this by D star. Here it is. Multiply this by D star. Fine? So you see, the gradient relative to x minus j times the gradient relative to y times 1/2, what do you get? That's what we define to be the gradient relative to z in the complex case. Remember when I introduced the Wirtinger calculus and I defined gradients in that domain, right? The gradient of a function relative to z, I defined it as 1/2, right? You compute the gradient of the function relative to its real component minus j relative to its y component, right? And similarly for z star, there was a similar relation, right? So this is exactly what you have. You see, this will have the derivatives relative to x minus j, the partial derivatives relative to y, times, so if you combine them, right, so actually you will get the gradient relative to z. And likewise for the second column, you will get the gradient relative to z star. So this product here will actually be this row vector, gradient relative to z, and then gradient relative to z star, right? Right? So if I go back, this is exactly this times the 1/2 d star. Go forward, and then I have to multiply by u minus u0. But u minus u0 is z minus z0, and then z minus z0 star transpose, right? So because they have to have the same dimension, right? Okay. So when I do this inner product now, you see, gradient times this vector, gradient times the same vector, star here, star here. What you'll end up getting is you'll get this inner product plus its conjugate. This will be the conjugate of that inner product. You understand? This inner product here is the conjugate of that inner product. So when you add them together, you get 2 times the real part of this times that. Okay? Okay? You'll get 2 times the real part of this times that. So when you do this calculation, you see what the relation becomes in the complex case. This is what it becomes. G of z is lower bounded by this function that you have here, this linear function that you have here, right? Except that it is 2 times the real part of that inner product. When we were dealing only with real data, you did not have the 2 real parts, right? So these differences come up. But now this is written completely in the z domain. Fine? Okay. So let me show you what happens for the other situation. And from this property, you can deduce the extension of the inner product property I showed you before, right? Before you did not have the real part, now you have the real part. And it makes sense because this inner product, now that you are dealing with complex data, it can be complex, you take the real part of it. So this is what holds now in the complex case, okay? So this real argument will appear repeatedly. Again, now the extension to strict convexity is similar, right? For strict convexity in the Z domain, this is less here. And the inner product property will have the real and that, right? So I don't need to spend too much time on this, okay. And strong convexity, if you write it first in the V domain, this is the property, right? In the real domain, right? This is the property. Now translate it. Okay, translate it. Well, this is G of alpha Z1, 1 minus alpha. All of these become G of Z's. V1 minus V2 squared. Remember, this is XY, XY. This distance is squared is exactly the difference between, right? So you can write it directly in the Z domain as well. So the definitions, they do not change. You can write them directly in the Z domain. What changes are these properties, right? The underestimation of G of Z. In the complex case, now you will get this real component appearing. That's what, right? That's what changes. Okay, the inner product now, because remember, G of Z is real. So you have to have real quantities here. So it makes sense that the real part will appear, okay? So that appears. And then the same quadratic growth continues to exist. Okay, so this is not, you can read it, it's not that different. And the inner product result now is lower bounded by this, just like before, okay? So this is the summary, the equivalent summary of before. Now, so when I'm dealing with complex data, you see the only difference is you get the real there, right? And there is one other subtle difference. This nu becomes divided by 2. Okay? Becomes divided because you had something like 2 reals, okay? So if your function is nu strongly convex, in the complex case you have nu over 2. In the real case you just have nu. Okay? So we are going to carry this 2 with us. Okay? When we start studying algorithms, what I'm going to be doing, okay, I will be introducing a variable h, which I call the type variable. It will be 1 if your data is real. It will be 2 if your data is complex, right? And I will always be always be writing this bound like this. I will be doing something like that, so that I don't have to worry, right? This h variable is there. We make all our derivations regardless of the type. The h variable will account for the type. If it's complex, you put h equals 2, and then your results are what you need to get, for, right? So I'm just trying to motivate right now why I will be doing what I'm doing later. When I tell, oh, let's introduce a type variable, now you know where it comes from, okay? This is one reason for it, okay? And then again, the same Hessian conditions as before. Because remember, I showed you in the last lecture that the Hessian matrix in the Z domain is similar to the Hessian matrix in the V domain, H of V, right? So in the V domain, if you need these inertia conditions to hold, these matrices to satisfy these conditions, right? Then the same thing will hold here. Okay? So you need this to be non-negative, this to be positive, and this to be larger than, again, mu over 2. Okay? So just to explain this a little bit more, if you write it in the V domain, in the last case, when it is strongly convex, you need H of V to be lower bounded by nu. But now if you transform H of V, if I multiply by d star 1 over 4, d star 1 over 4, nothing changed. And the reason I do that is because this becomes the complex gradient. Okay, and this is 2, becomes nu over 2. So that's why the 2 comes up. If you write it in the V domain, you don't have a 2. The reason the 2 comes up is when you translate your condition to the Z domain, right? But we are going to take care of all of this later so that we don't have to worry in our minds. Is there a 2 or is there not a 2, right? I will just introduce this type variable h, right? And it takes care of everything. If h is complex, it will be 2. Otherwise, it is 1. In this example, what's the Hessian matrix of the quadratic cost function? No? Okay. C transpose, right? It's 2m. Okay. So it's lower bounded from below by lambda min of C. In the real case, it was 2 lambda min of C. Okay. So this is strongly convex, right? Okay. Okay. So I'm going to take a 1-minute break here before we continue. Okay. Thank you.
Define over a scalar, please. This function is not complex. Take any 2 points. The value, right? So you have to hold it. The value
Okay. Welcome back to EE 210B. So I'll be talking about logistic regression. If you remember, last time I showed one of the functions when I was giving an example about convex functions or strongly convex functions, and I mentioned the logistic function, and since it will come up time and again in our examples, I want to motivate it to you quickly. Okay, some of you may have seen it already, but others may not, so let me motivate it to you very quickly. Okay, this is the reference for this lecture, Appendix G from that text. Okay, so let's assume that you have binary variables gamma. Sorry, let me go back. I have binary variables gamma. They can be +1 or -1, and feature vectors h. Okay, so this language that I'm using is in the context of learning algorithm, right? Pattern classification algorithms. Assume I have a collection of feature vectors h of dimension m each. Okay, for example, the entries of h could be your height, your weight, and gamma could be whether you are female or male, right? That's an example of a pattern classification problem that I'm interested in. Okay, so logistic regression is one useful way. There are many other ways, but this is one useful way for you to solve pattern classification problems of this type. I give you an H, first you train the system. I give you many H's with the corresponding gammas. You train a system, and then I give you a new H. Tell me, is this person a male or a female? What's your best guess, right? Based on this feature vector. That's what logistic regression will help solve for you. This is different from the regular linear regression problem. If you remember, let's keep everything scalar. In linear regression, you have two variables, let's say x and y, and you have multiple measurements, right? Let's say x is weight, y is height. And this will tell you how they are correlated. I give you a future height, and then you try to guess what would be the best weight for that person according to a linear regression model that you fit into the data, right? So that's the standard linear regression. In logistic regression, okay, one of the variables is binary. Gamma now is binary, right? Even when h is a scalar, all we are saying is that, okay, when h is a scalar, let's say, or even let's say h is in the plane, so this is the first entry of h, second entry of h. I'm telling you that some of these entries correspond to male individuals, other entries, let's say, correspond to female individuals. That's what I'm telling you. And then I would like you to develop a procedure such that if I give you a future h1, h2, you can tell me whether that person belongs to one class or the other. So how does logistic regression solve this? I mean, the logistic regression formulation, how does it solve a problem like this? Okay, this is just a way to motivate logistic regression. There are many ways to motivate it, and it's not the purpose of this particular presentation to explain everything you need to know about logistic regression and its application to learning. You learned that in 210A. Here, I just want to use it as an example that will live with us throughout this course. Whenever I want to illustrate something, I'll come back to this function, okay? So in logistic regression, what we do is the following. We are going to assume that the probability distribution of class 1 given the data, okay, is a logistic function of this form, okay? W0 is some parameter vector you don't know. H is your feature vector. And we are going to assume that the distribution follows this logistic distribution, okay? I will show you an example. Now, since I only have two classes, the probability that gamma is -1 given the h is 1 minus this term, right? If you do that calculation, it will be 1 over 1 plus e to the hk transpose omega 0, right? This minus here becomes plus here. That's all. Okay. Here it is. Okay. So logistic regression assumes that the conditional PDFs, the distribution of one class or the other, given the feature vectors, follows this distribution, okay? Now, why are these distributions useful? Let me illustrate it for a simple example. Let's look how this logistic function, 1 over 1 plus e to the x and 1 over 1 plus e to the minus x look like. Let's look at how these functions look like. They look like this. For example, this is how it looks like when the class is +1, you have a minus. And this is how it looks like when the class is -1, you have a plus. So what this is saying is that under class 1, this type of behavior is more likely to be seen than this type of behavior, right? I'm more likely to see, of course, this is normalized, right? Because we centered everything. This is just an illustration. This is a scalar, not H transpose omega, okay? Whereas in the other case, this type of data is more likely than that type of data. So the choice of logistic functions allows you to model this, right? This dichotomy in the classes, right? To tell you that certain types of feature data are more likely under one class than the other class and vice versa, right? Okay, so this is what the choice of the logistic function tells you. Okay, so now, the conditional PDF, given the feature data, I can write it in a single expression rather than writing it for each gamma. Right? I can group them together into a single expression. When gamma is +1, this becomes minus. When gamma is -1, this becomes plus, right? Okay, so in the logistic regression model, this is what I assume. I assume that my conditional distribution of the data follows the logistic function that you have here for some omega 0 that I don't know. I give you many gammas, many h's, your job is to estimate omega 0. Once you estimate omega 0, I will show you how you can use it to tell me whether a new h I give you belongs to one class or the other. How? Let's assume that you already know the omega 0. I'll show you how to find it. Let's assume you know omega 0. Okay? If you know omega 0, then you can compute this probability, right? You have the logistic function. And you can therefore compute the probability of it being +1 or -1 and find out which one is more likely. Let's say if this probability is 0.8 and this probability is 0.2, 0.8 over 0.2, that gives you 4. So this one is 4 times more likely than that, then you declare for that h that my gamma is 1. All right? So if you define the odds ratio, this odds ratio then, if it is larger than 1, you say it belongs to one class. If it's smaller than 1, you say it belongs to the other class, right? Or you can work with the log of this ratio, right? Because then the log of the ratio, log of 1 is 0. So all you really need to say is that if the log of this odds function is larger than or equal to 0, it belongs to one class. Otherwise, it belongs to the other class, right? Okay, so here it is. You can define the logit function, which is the log of the ratio. Fine? Okay. Now, what's useful about this function is that entries in class +1 will have, let's say, non-negative values for the ratio, for the logit function, and entries in the class -1 will have negative values, the opposite values, right? +4, -4, log of, okay? So, once you find omega 0, you evaluate this function. If it is larger than or equal to 0, you say I belong to class +1. If it is less than 0, you belong to class -1. That's the idea, okay? Now, if you replace P by what it is, I told you earlier that P is this exponential minus H transpose omega 0, right? And compute this log, you will find that this function becomes linear in omega 0, right? Linear in omega 0, okay? So what the logistic regression problem is doing is the following, right? It's finding a linear model for the logit function, right? It's finding a linear model for that function, okay? Okay. So how do I find omega 0 now, okay? How do I find omega 0? There are many ways to motivate it. For example, you can use a maximum likelihood formulation to arrive at the expression I'm going to show you. Here I want to do it in a more direct way and motivate it as follows, okay? So I would like to find a vector omega 0 such that when I compute the inner product between omega 0 and h, if I get a non-negative value, I say you belong to one class. If you get negative value, you belong to the other class. So how do I find omega 0? Okay. Well, one way to find omega 0 is as follows. You are trying to fit a model, a logistic right, regression model to your PDF. Okay, so you are trying to fit a model of this form to your PDF. Okay, you don't know what the unknown PDF is, right? So you have some unknown PDF that you don't know, and you are trying to fit a model to it. Okay, you are trying to find an omega such that the logistic PDF that you have is a good approximation for the unknown PDF. One way to measure how close PDFs are to each other is by using the Kullback-Leibler divergence measure. What is that measure? You compute the expected value of the log of the ratio of the PDFs. That's one measure. Okay, so if I try to minimize this, okay, if I try to minimize this over omega, the unknown, the numerator does not interfere, because, right, it doesn't depend on omega. Try to minimize this over omega, so what you have to do, right, the gradient, okay, sorry, you have to minimize this over, I can write this as the expected value of the log of the numerator minus expected value of the log of the denominator, right? The numerator doesn't depend on omega, so minimizing it over omega doesn't matter, so I'm left with minimizing this over omega. If you minimize that over omega, and remember, P has the form 1 over 1 plus e to the minus gamma h transpose omega. Then the log of that becomes minus the denominator, and that minus cancels this minus, and you end up with this function, right? So this is the logistic function. That's how it comes up. Okay, this is the example I showed you before. I showed you this function without the expectation. Okay, I introduced it like that, but this is where it comes up. Okay, so what this argument shows is the following. Okay, if you have data gamma k, hk, many feature vectors belonging to different classes, and I give you, and you would like to determine a learner, which is parameterized by a vector omega, such that when I give you a new feature vector, you can use that omega to tell me whether it belongs to this class or that class. This is how logistic regression does it. What logistic regression does, it minimizes this cost function over the distribution of the data, right? Because there is an expectation here. So if you know the distribution of the data, you can compute this expectation, minimize it over omega, that gives you the best omega that you want under this criterion, right? Once you have the omega, then you compute the inner product of any new h with that omega, right? And declare it to be in one class or the other depending on the sign of that inner product, right? Obviously, in general, we don't know the PDF of the data, right? So you cannot really minimize this explicitly. We are going to develop gradient algorithms, right? Similar to what you have seen in the single agent case, right? In E210A, we are going to go deeper into this in this class, okay? So we develop algorithms that can seek the minimizer of cost functions like this, even when you don't know the distribution of the data. Fine? So this short lecture is only meant to motivate the logistic function, because you will see it a few times more in your examples and also in some of your homework problems, so that it makes sense to you that a cost function like this is meaningful. It solves a meaningful problem. Okay, it's trying to find a W, okay, such that you fit a logistic model into the feature data and the class data that you have to help you classify future feature vectors. You understand it, right? So that's what the logistic regression model is, okay? Very good. So I'm going to stop here and then continue, okay? Half a minute break, okay? Okay, welcome back to EE210B. Okay, let's continue our discussion of the background material, and today I want to introduce you to mean value theorems. We are going to use this a lot in our derivations in future lectures. You may have seen some of it, but maybe not. Okay, so this builds up on the lecture on convex functions. Okay, so I'm going to use sorry, not this particular lecture. A future lecture will build on that, but not this one. So the reference for this material is Appendix D from my text, the one that I showed you earlier, okay? So again, what I want to do here is the following, okay? You all are familiar with Taylor series, right? If I have a function f of x and I want to approximate it around f of x0, around the point x0, what do? You say f of x is f of x0 plus a linear term plus a quadratic term, and you can continue. But at some point you stop, right? That is an approximation, right? And you will have error terms that you ignored. So that's one way to approximate a function around a point. Okay, the results I'm going to show you now are going to give you an approximation where the approximation actually, it's not an approximation, it's an exact expression without ignoring terms. Okay, and these exact expressions given in the form of mean value theorem expressions will be very useful for us, because when we study the performance of algorithms over networks, I will need to take some functions and approximate them in the form you're going to see, and keep control under check the size of the errors that are there in my expression. So I need to know what they are exactly. And to know what they are exactly, these transformations that I'm going to show you will be more useful for us than using Taylor series and throwing away terms that you don't really know, okay, how to control. Okay, so let me explain to you what I mean, okay? So again, my function is real valued, sorry. My function is real valued, okay? And I'm going to assume it to be differentiable whenever needed. Again, I'm going to deal with real data or complex data. I'm going to introduce the results for the real case, and then you're going to see the extensions for the complex case in a very similar way to what I did for convexity, okay? So take a function g of z, where z is a real vector, fine? And let's define a function f of t like this. So z0 is some point in the domain of g. I perturb it a little bit. T is a small scalar, or a scalar between 0 and 1. Okay, I perturb it a little bit. So f is a function of t. Okay, so f is a function of a scalar argument. G is a function of a vector argument, right? So I transform a vector argument into a scalar argument, okay? Fine. Why do I do this? Look here. So what's the value of f at 0? It is g at the initial point. What is the value of the function at 1? G at the end point, right? Remember, I'm not assuming G to be convex here, right? I didn't say anything about whether G is convex or not. Later, I'm going to do this in a future lecture, okay? For now, this is general, okay? I only need this G to be differentiable for the results I have here, okay? So I have some function, right? So I have a function G. This is G at Z0, and this is G at Z0 plus delta Z, right? F of 0 captures one, F of 1 captures the other. Now, you know very well from the fundamental theorem of calculus, right, that this difference, F of 1 minus F of 0, is the integral of the derivative of F between 0 and 1, right? That far you know. Okay, very good. But what is the derivative of F with respect to time? Or with respect to T? T is not necessarily time, okay? So F is a composite function, right? F of T is G at Z0 plus T delta Z, right? So differentiating this relative to time, relative to T, okay? I'm differentiating this relative to t, so the way you can do it is you can differentiate the argument relative to t, that gives you delta z, and then differentiate the function relative to z, right? Okay, here it is. Evaluated at that point, right? This is composite differentiation, okay? Now, why do I do this? Because now I'm going to come back to this fundamental theorem of calculus, replace f of 1 by the endpoint, f of 0 by the starting point, the derivative by the gradient vector. Right? This is a column, delta z is a column, gradient is a row, so this is an inner product, right? A scalar, put it here. I get my first result. Okay, this is my first result, my first mean value theorem. Okay, you may have seen mean value theorems in the scalar case, okay, but what this is saying, this is what I was referring to earlier. If I want to approximate a function around a point, z0, I can write it, this is equal to that plus, and I know exactly what the difference is. It's useful for that reason, okay? If I want to approximate a function around a point, so this is that value plus something which I know exactly, and it depends on the gradient vector. Okay, and if I happen to have bounds on the gradient vector, for example, I can bound this integral. Okay, fine. So this is an integral of the gradient times delta. Fine so far. This is our first theorem, our first mean value theorem for the function. Now, this is for the function. I can find a similar relation for the gradient of the function, because you see, this is the function, scalar valued. The function is real valued, right? If I compute its gradient relative to z, that gradient will be a vector. Let's say gradient relative to z transpose will be a vector. Each entry of this vector is a function, right? So for each entry of that vector, I can apply a relation like this. The first entry of the gradient vector, the first entry of the gradient vector, right? And here, what it will be, the gradient of that first entry relative to z, right? I can apply this relation to every entry of that gradient vector. Then I will end up with a vector minus a vector. These are the gradient vectors. And here you will end up, right, with the Hessian, right? Because the functions here are gradients already, right? And this is the gradient of the gradient, so it becomes a Hessian. Okay, that's how you get the second result. Okay, so this, to do it slowly, okay? Here it is. So let's define H to be the gradient. So this is a column vector. Now I apply the mean value theorem to every entry of this column vector, right? Okay. So here it is. Every entry, okay? And then here you will have the gradient of these entries of H, right? Okay. But the gradient of H, and H is already a gradient. So that becomes the Hessian, right? So it's not difficult. This is a simple argument, right? And you see, this is the gradient relative to z transpose. Here I just transpose them because I want to write them relative to z. So that's why this delta z now appears there, because I transpose the relation, right? So this is the mean value theorem for gradients. So now if I want to approximate the gradient at a point, I know exactly the difference. It will involve the integral of the Hessian. Right? So this is how I will be using these results later, okay? This is the statement here. That's it for the real case. The mean value theorem for the function, all I really need here is for the function to be twice differentiable, because I need the first and second order derivatives, that's all. Okay? So this is an expression for the mean value theorem applied to the function, mean value theorem applied to the gradient. Since the gradient relative to this column z is a row, then you have delta z transpose first here, a row. The Hessian is a matrix, right? So row times a matrix, it's a row. So it's consistent in dimensions, right? That's why the delta z appears there and not here. Okay, here I called t, here I called it r. Just, you understand where these relations came from? They're not difficult. And I will be using them to perform approximations like this. For example, if z0 happens to be the z superscript o, which is the minimum of g, remember my notation, then this term will disappear, right? Okay, very good. So let's do the extension to the complex arguments. Very similar, okay, not that difficult. Okay, again, if I have a function g of a complex argument, right, think of it as a function g of a real argument v, right? And then you write down the mean value theorems for g of v, for the gradient of g of v, and then translate them to g of z, gradient of g of z, like I did, right, when we studied convexity. That's all. So that the final results are stated in terms of the z domain, not the v domain. Understand? That's all I'm going to do, okay? Okay, so this is here. This is the column x, y. This is the column z, z star transpose. And you already know how to go from u to v, right? Or return back. These are the relations that take you from one to the other, right? That's what these relations are saying. Okay. So let's derive the results, okay? Let's write down the mean value theorem using the v domain, v, right? V, here it is, right? Now let's translate this into the z domain. G of v0 will be g of z0. This will be g of z0 plus delta z, okay? Here, remember that u is dv, right? Or v is 1/2 d star u, right? So this delta v is 1/2 d star delta u, right? Delta u. Delta u is delta z, and then delta z star transpose, right? Just the same argument I used in the convex case. Are you following? Okay, I'm doing it slowly, right? And then remember, the gradient of v, it used to be gradient relative to x of g, right? And gradient relative to y of g, right? At this argument here, right? Times 1/2 d star, right? And you remember I did the same calculation when I was studying convexity in the complex domain, right? Do you understand that? Okay, I have it on the next slide. Okay, so this gradient relative to v, here it is, times d star times 1/2. I showed you that it is the gradient relative to z, the gradient relative to z star. Remember? This is what we showed when we studied convex functions in the complex domain. We showed that d star times 1/2 times this gradient is this. And delta u is delta z star transpose. Now compute the inner product again. You see? This times that is the conjugate of this times that. You will get the 2 real part of this times that. Again, the 2 real part comes up, right? Okay. There it is. You see, this is the extension to the complex case of the mean value theorem. Right? 2 real part comes up because these are real valued functions, so it makes sense for the 2 real part to come up. Understand? Again, I'm going to use this to approximate this around z0 and know exactly what the difference is. Okay. So let's do the next one now. The mean value relation for the gradient. Again, if I write down in the v domain, this is exactly what we derived before, right? In the v domain. Gradient relative to v, the Hessian relative to v, right? Now transform this to the z domain, right? I know how each one of these is related, can be expressed in terms of the gradient relative to z. This is what I just showed on the previous slide, right? Here. Gradient relative to v, right? Follow this, right? Each one of the gradients relative to v, okay, let me do it slowly. If you come back, if you go here, if I multiply by d star from the right, times 1/2 here, right? Each product, the gradient relative to v times d star times 1/2, right, will give me a relation like this, gradient relative to z, gradient relative to z star, right? Are you following? Okay. So this actually will give me something that involves a gradient relative to z and a gradient relative to z star. Okay? Fine? Because you see, this is gradient relative to a row, I get a column. Okay? And the first term also will involve a gradient relative to z, relative to z star. This one will be evaluated at z0. This one will be at z0 plus delta z, right? I'll show the details on the next slide. I'm just motivating it. Okay, so I had to multiply by d star, okay, from, sorry, here I should have multiplied by, from the left, you see, if you go back, because this is, okay, gradient relative to v times d star from the right, okay? I should have multiplied it by the transpose of it from the left, actually, right? Because the gradient relative to v transpose, right? So I should have multiplied by d star transpose, 1/2 d star transpose from the left, okay? It's just a simple calculation that I'm sure you can do, okay? So not from here, but on this side, okay? Okay. So I multiplied on this side, right? And then remember, I can put here again d star d 1/2, right? To transform this to delta z star, transform this to the, right? Because once you have d and the Hessian relative to v, you get the Hessian relative to z. Remember? Okay? Okay. So look at the last relation. This is what you would get, right? You see the vector that I showed you before. The vector that I showed you before, I may have written it wrongly. It is relative to z star, z transpose. Just make sure the transposes and the stars are correctly, but you get the idea, right? Okay, but you get a vector, you get a vector, you get the Hessian of z, and you get the vector of delta z's, right? Now, what's interesting about this is the extension of the mean value theorems to the complex case, right? Okay. In the real case, I don't have this. Fine. In the real case, I only have one line. I only have the gradient relative to z, the gradient relative to z, and the Hessian. But in the complex case, you have to extend your gradient vectors, right? You have to extend the gradient vectors. And remember, the Hessian matrix itself is 2m by 2m, is twice as large, right? So you have coupling, right? You have coupling here. You see, because this Hessian matrix in general is a block matrix, right? So you're going to see the implications of this later when we study networks. I'm just calling your attention to these facts. For now, this is just a mathematical result, but later when I use it, you will see how this impacts the performance of the network, okay? If the Hessian of G is block diagonal, for example, G is a quadratic cost, the Hessian will be CC transpose. This becomes block diagonal. I can ignore the second row and write the second relation only as this minus this equals the top part times delta z, right? It collapses to only one line. But if this is block diagonal, right, then the approximation of the gradient at this point also depends on the value of this other gradient. Not just on that, but on this other grade. These are two different things in the complex case, right? These are two different things in the complex case. You understand what I'm saying? Okay. So the mean value theorems are simple. They are just these results that I showed you, the real case and the equivalent complex case. But the interesting thing is that you saw it already last time, right, in lecture 2, right? Lecture 2, I have to keep track of that. Okay. You saw that the Hessian matrix is block diagonal, right? And for Hessian matrices in the complex case. And here you are seeing one implication of that. When I write down the mean value theorem for the gradient vector, it couples the approximations of these two gradients. Okay? And this is the example. If my cost function is quadratic, the Hessian is block diagonal, then you throw away, for example, the second line, and you just write down the first line. The first line involved gradients relative to z star. I conjugated and I wrote it relative to z. Okay? So for a quadratic cost, this is exact. Right? Here it is. The gradient at this is the gradient at z0 plus the step that you took times the Hessian matrix. Okay? And actually you don't need, by the way, you don't need all these fancy arguments to arrive at this conclusion for the quadratic case. For the quadratic case, you know exactly what the gradient is, right? Evaluate it at any point z0, evaluate it at any point z0 plus delta z, subtract, you will get that. In the quadratic case, you can do it directly. But of course, the mean value theorem is useful for general cases, right? When my cost is more general, for example, try to do this for the logistic cost. Right? So the mean value theorem will give you an approximation. Not an approximation, will give you the expression, right? The exact expression. Okay? Good? Any questions? Okay. So I'm going to stop here today, okay? Continue next time.
Mean value terms derived by any other name in theory? Other names for them?
Okay, of course. Did the professor say how many people can form a group?
It depends on the complexity of the project. That's just
Complexity, okay.
yeah, there are about 10